when you're dealing with three-dimensional shapes, one of the measurements that's associated with it, of course, is surface area. It's about how much it takes to cover an object. But three-dimensional shapes also have another measurement called volume, and instead, this is all about how much it takes to fill the object. So, our objectives include being able to use formulas to find the volume of prisms, pyramids, cylinders, cones, and spheres. And then our second objective, do you remember probability? Do you remember applying probability to geometry with lengths and areas? Well, we're going to do the same thing, except for with volumes. Well, let's go ahead and get started with a warm-up question. Find the volume of the given figure in cubic units. So remember, when you measure area, it's in square units. When you measure lengths, it's in linear units to the, say, first power. And volume is in cubic units. It's a three-dimensional form of a measurement. All right, so volume, about how much it takes to fill an object, is essentially asking how many cubes it would take to make up that object. So all I got to do really is just count these things up. Like, for example, I can go 1, 2, 3, 4, 5, 6, 7, 8. Oh, but what am I supposed to do with these, like these two halvesies that are right up top here? I could put both of them together, like we've done with composite figures. Just put this thing over with that one to make a whole one. So that would make, what, 9? And then I'll do the same thing with this one down here. I'll put that together with this one to make 10. So in this top layer, there's 10, but there's, well, I can obviously see there's 2 layers deep. So I'm just going to multiply that 10 times 2. I get 20. 20 cubic units. That was not a cube. That is, here it is now. Saved it. Okay, so essentially what we have here is a prism. I do believe that it is an octagonal prism because the shape of the base here is an octagon. And notice that what we did here, in order to find the volume in cubic units, look at that 3 right there, cubic units, is to measure the area of this base face right here. Measuring the area of it was telling me how many cubes make up that layer. And then it was 2 deep, so multiply it by 2, and 2 is essentially the height of that. So basically what we did was we multiplied the area of the base times the height. And that is a general formula for volume that's going to work for so many figures, any kind of prisms and any kind of, let's say, a cylinder, shapes like that. Okay, so before we actually get into all of the different formulae for volume, let's take a look at the activity, the investigation that we're going to do, which involves making a box and calculating its volume. As you may be aware, Knox is in want of a roomy box for both his dirty socks and his pet fox. Do you remember the Dr. Seuss book? Knox on Fox on Box and whatever it's called. It's supposed to be a tongue twister. Okay. But how will you make said open box to hold those socks and the most blocks or clocks for Knox and his fox? Be it a silly caper to fold a piece of paper into a voluminous container for socks or a skyscraper? What are we even talking about? Okay, so essentially what we want to do is we want to make a box. We're going to make a box out of a piece of paper. Here, let's take a look over here. I'm going to scroll down here just a little bit. We're going to take a piece of paper, regular 8.5 by 11, a sheet of paper, and we're going to cut a square from each one of the corners there. Where are you going? Okay, the same size square from each one of the corners. It's going to make a net. We're going to fold up the sides, as you can see here on number 2, tape the edges together, and it makes an open box, a box with no lid. Okay, enough to, put blocks in there and socks and maybe even a pet fox or something like that. Okay, so whenever you go to make your box, everybody's going to be making almost essentially a different sized box. A lot of times when students see this kind of net for the first time, okay, I got an 8.5 by 11 sheet of paper. Sure, I can probably make different size boxes, but it's always going to have the same volume. Is that true? That's what we're going to find out. Okay, so to make your box, you have a specific square size that's going to be assigned to you. What size you are going to cut from each one of these corners to make the net of your box. Okay, if you scroll down just a little bit on Canvas, you're going to see a whole bunch of, it's asking you to log in. So maybe I come down here to authorize. It's going to ask me to sign into my Google account. Let's see, my password. Please don't try to memorize all of these dots right here. Boop. All right. And then I will authorize it and allow it. Okay, so now it's embedded right in here. So you're going to, no, I am not interested. Got to go all the way back down again. All right, find your class down here. Here's 8th grade. Here is first period. You can scroll through these little tabs at the bottom to pick your particular class. Find your name. It is alphabetized by first name. Here's the square length that might be assigned to you. You're going to cut your net based on that square length. So this one, for example, is 0.75, so 3/4 of an inch. You're going to cut that 3/4 of an inch from each one of these corners, a square with that side length. Fold it up, make it, and then measure its volume, and then you come back to this and you actually type your volume. So, I mean, I would come in here, and whatever my volume is, I'm going to type it in there. And this is a shared document, so when we get back to class, we'll be able to see everybody's different volume calculations, and then we're going to do something special with that. So that, remember, our goal really is, hey, what size box is going to give us the most volume? That's going to hold the most clocks, blocks, foxes, and, you know, whatever else that we choose to put in it.